Good afternoon, students. So in this lecture we'll discuss the Fermi level in the case of intrinsic semiconductor. This lecture, it is the part of the previous lecture, so we can say that this is lecture 12 and this is part 2 of that lecture. So in this lecture we will study about the position of the Fermi level in the intrinsic semiconductor, that where this Fermi level it lies in the intrinsic semiconductor. It lies close to the conduction band, or it lies close to the valence band, or it lies in the middle of the both. So as we know that in case of intrinsic semiconductor, the number density of electrons is equal to the number density of holes, because the number of electrons that will move from valence band to conduction band, they will leave the same number of holes in the valence band. So the number density of electrons is same as that of the number density of holes in case of intrinsic semiconductor. And we have derived the expression for Ne yesterday, and that is equal to this, and the expression of NH, that was equal to this. So here this 2 will be cancelled out, this 2 pi will be cancelled out, this h square will be cancelled out, and this kt will be cancelled out, and we're left with these 4 terms. And from this equation what we have to calculate? We have to calculate Fermi energy or Fermi level, that is EF. So we have to keep this EF on one side and all the other terms on the other side. So for that we'll do some calculations. Now move this term to this side, it will move to the denominator, and move this term to this side. So we will get this equation. And after this, move this to the numerator, base same, and they are in the division, so powers will be subtracted, and what we will get, it is e raised to power EF minus EC by KT. This term will be subtracted from this, so signs change होंगे. So EV जो है, it will become negatively charged and EF will become positively charged. So here we will have minus EV plus EF upon KT, and this is equal to MH star upon ME star raised to power 3 by 2. Here this EF plus EF, it will become 2EF. So e raised to power 2EF minus EC minus EV upon KT, it is equal to MH star upon ME star raised to power 3 by 2. Now take natural log on both sides. So after taking natural log on both sides, we will have this so then apply the formula of log m raised to power n. We will get, on applying the formula of log m raised to power n, that is equal to n log m. N log m, again here n log m, this term, this is equal to 1, and we have to calculate the value for EF. It means move this KT to this side. We will get this term 2EF minus EC minus EV, it is equal to 3 by 2 KT log to the base E MH star upon ME star, and then EC and EV, these are negative on this side. Move these two terms to this side, they will become positive, and this 2, it is multiplied with this EF, and on moving this 2 to this side it will be divided. So we will have this EF, it is equal to EC plus EV. This 2, it will be divided here, it will be in the denominator on right hand side, plus 3 by this 2, and this 2 will be 4 log to the base E mH star upon me star. This is the required expression for Fermi level. But in case of intrinsic semiconductor, hole is an empty space created by electron, so their mass will be same. So if this mass of effective mass of hole, it is equal to the effective mass of electron, then it will be cancelled out, and this log to the natural log of 1 is 0. So this will become 0 in intrinsic semiconductor. In intrinsic semiconductor, if mass of effective mass of hole, it is same as that of the effective mass of electron, then this log to the base E mH star upon me star, it will be equal to 0. This implies that this EF, it will be equal to EC plus EV by 2. So from this we can conclude that in case of intrinsic semiconductor, so from this what we can conclude, in case of intrinsic semiconductor, Fermi level lies in the middle of conduction band and valence band, because it is the mean or the average of EC and EV. It means it will lie in the middle of conduction band and the valence band in case of intrinsic semiconductor. So in the next article, we will derive the density of electrons, or you can say that concentration of electrons in the conduction band and holes in the valence band in terms of band gap, that is Eg. So till now we have derived the expression for Fermi energy EF, that is given by this equation 1. We have derived the expression for the concentration of electrons and holes, that is equation 2nd and 3rd. Now we have to derive these two expressions but in terms of Eg. So how we will convert these two expressions in terms of Eg? We will use this EF. As we know that in this term of NC, we have EF minus EC by KT. So what we will do, from this equation 1, we will subtract EC on both sides. So we will get EF minus EC here. But we will subtract EC from this equation from both sides. After that, we need EF minus EC by KT. So then we will divide this EF minus EC equation by KT on both sides. And we will get the value for this EF minus EC by KT. So minus EC from this side and minus EC from this side. This. Then divided by KT on this side, both the terms. So this KT and KT will be cancelled out. Take LCM here and we will get EV minus EC by 2. So we'll get this equation. And as we know that the forbidden gap Eg, it is equal to the EC minus EV. When we subtract the top of the valence band from the bottom of the conduction band, then we'll get the forbidden gap, that is Eg. But here we have Ev minus Ec, so that will be equal to negative of energy gap. So put this value in this equation, we will get this expression. So now we will put this value in the expression of Nc. So the expression of Nc will become this. And now we will solve this. So Nc, it becomes equal to 2 into 2 pi me star kt upon h square raised to power 3 by 2 e raised to power minus eg by 2 kt e raised to power 3 by 4 natural log mh star upon me star. Now here this is n log m, so it will become log m raised to power n. This term, it will become e raised to power natural log mh star upon me star raised to power 3 by 4. And this is equal to 1. So we will left only with this mh star, me star raised to power 3 by 4. So this equation, it will become Nc, this is equal to 2 into 2 pi kt upon h square, and here we were having this me star, keep that term separate, e raised to power minus eg by 2 kt and mh star raised to power 3 by 4 divided by me star raised to power 3 by 4. In the next step, 2 into 2 pi kt upon h square raised to power 3 by 2. Here this base same and powers will be subtracted out. So this will become me star raised to power 3 by 4 and we will get this expression. So this is the expression for the number density or the concentration of electrons in the conduction band in terms of forbidden gap Eg. Suppose this equation as star. Now we have to derive the similar type of equation for NH, and for NH we need the value of Ev minus Ef by kT. So what we will do now, from Ev we will subtract the equation of Fermi energy, that is equation number 1, from both sides. So we will get Ev minus Ef, and here Ev minus right hand side of the equation of Ef. Then divide it by kT on both sides. This kT and this kT, it will be cancelled out. Here after taking LCM, we will get Ev minus Ec by 2 kT. So we'll left with this. So now we will put this value in the expression of NH and we will get this equation. Now we will solve this equation to get the desired expression for this NH, and it is two pi kT upon h square raised to power 3 by 2 mh star raised to power 3 by 2 e raised to power minus eg by 2 kT e raised to power minus 3 by 4 natural log mh star upon me star. Then apply the formula of, here apply the formula of e raised to power n log m, it is equal to this log m raised to power n, and this is equal to 1. It means we're left with NH, it is equal to 2 into 2 pi kT upon h square raised to power 3 by 2 mh star 3 by 2 and take its reciprocal. This minus 3 by 4, it will become plus 3 by 4. So this me star by 3 by 4, mh star 3 by 4, e raised to power minus eg by 2 kt. And move this to the numerator, base same parts will be subtracted out. So 3 by 2 minus 3 by 4, this, it will become mh star 3 by 4. And we will get this required expression. So this is the expression of number density of holes in the valence band of the intrinsic semiconductor in terms of band gap. So next comes the law of mass action. So from this you can clearly see that this expression for NH, it is exactly same as that of the expression of Ne. So Ne, it is equal to NH in case of intrinsic semiconductor. So multiply these two expressions of Ne and NH, we will get the product of Ne and NH. It is equal to this. And as electrons are negatively charged, so suppose Ne is N and holes are positively charged, so NH as P. And this product, as both are intrinsic carriers and both are equal, suppose this N and P, it is equal to Ni. So this product N and P, it will be equal to Ni square. And at any given temperature, the number this N and P, it will be constant at any given temperature. It means the product will be constant, that is equal to Ni square. And now when we add impurity to this semiconductor, intrinsic semiconductor, so suppose we are adding N-type impurity, then number of electrons will increase and number of holes will decrease. But this product NP, it will remain constant. So in this expression, if we are adding impurity to the intrinsic semiconductor to increase its conductivity, and suppose we are adding N-type impurity, then number of electrons will increase and number of holes will decrease. It means if N will increase, then this P will decrease, so that this product NP, it will remain constant, that is equal to Ni square. Similarly, if we are adding P-type impurity to the intrinsic semiconductor to increase its conductivity, then if number of holes in P-type semiconductor, it will increase, that is, if P will increase, then this N will decrease, so that this product NP is again constant, that is equal to Ni square. And this is known as law of mass action. So this law, it gives us about the relative concentrations of holes and electrons in case of semiconductors. So this I have already told you. So from the expression of this NP is equal to Ni square on the previous page, it is clear that there is no EF on the right side. So NP is equal to Ni square, it is independent of Fermi energy. But as there is Eg on the right hand side, so it depends upon forbidden gap. And this we have already discussed. Next topic is that what is the variation of electrical conductivity and resistivity of a semiconductor with temperature. Or you can say that what is the expression of electrical conductivity in terms of band gap. We have already derived the expression for electrical conductivity of intrinsic semiconductor in the previous lectures, and that comes out to be sigma is the conductivity, E times the number density of electrons multiplied by the electron mobility plus the number density of holes multiplied by hole mobility. And as in case of intrinsic semiconductor, this Ne and NH, they both are equal, as we have already proved and derived it, that suppose equal to Ni. So Ni and Ni, take this Ni common and you will get this expression. And now put the expression of Ni in terms of band gap, which we have just derived in this equation. So we will get this expression. And in this expression, From this expression we can conclude that what will be the variation of conductivity with the temperature in case of semiconductor. But on the right hand side there are three terms which vary with the temperature. One is mobility of electron and hole, it varies with temperature. Second, this T3/2 factor, and third is this exponential factor. All these three terms, factors, they vary with the temperature. But we have to check that out of these three factors, which factor will dominate. And the variation of this conductivity, it will be according to that factor which will dominate out of these three. So what happens is that the temperature dependence of this factor, of this mobility, it gets cancelled out with the temperature dependence of this factor, this T3/2 factor. Because of that, the only factor left is this. So in case of conductivity, this exponential factor, it dominates over these two factors. So the effect of these two factors, it will be cancelled out. It means so all these terms can be taken as constant. So our sigma, it can be written as constant into this term. Now to check the variation of sigma with temperature, take natural log on both sides, that is log to the base e. What we will get? Log to the base e sigma, log to the base e constant, plus log to the base e of this term. And we know that log m raised to power n is n log m, and log m is here actually log to the base e of e, natural log e, that is 1. So we'll get this equation, and this is the equation of straight line, because this, if we plot this along y-axis, this will be the intercept, this minus Eg/2k, it will be the slope, and this 1/t, it will be along x-axis. So this is the equation of straight line. It means the graph between log of sigma and 1/t, it will be a straight line graph with negative slope. So from this we can conclude that along x-axis, as this 1/t, it increases, 1/t increases along positive x-axis, it means t will decrease. And from this slope, it is clear that as this 1/t, it increases, natural log sigma decreases. It means sigma will decrease. So from this we can conclude that when temperature decreases, sigma decreases, and when temperature increases, sigma increases. So electrical conductivity of the semiconductor, it varies linearly with the temperature. Now what will be the behavior of resistivity with the temperature? And we know that resistivity is the reciprocal of conductivity. So take the reciprocal of the expression of conductivity, we will get the expression for resistivity. Now again take natural log on both sides, we will get this expression. And again we have the equation of straight line. If we plot this along y-axis, this will be the intercept, this Eg/2k will act as slope, and 1/t will be along x-axis. So this will be the graph. As the slope is positive, it means the slope is positive. The curve will increase linearly. So as we will increase this 1/t, rho also increases. And increase in 1/t means decrease in t. So t decreases, rho increases. So we can conclude that when temperature is increased, resistivity is decreased. So with the increase in temperature, resistivity of the semiconductor decreases and its conductivity increases.